So finally, we will be starting off with the bit manipulation playlist. Before that, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So as you can see, we will be covering up a lot of things in this particular video. So without waiting, let's get started. So the first thing that I'll be covering up is binary number conversion, 1's and 2's complement. So first of all, let's understand one thing. You must have done this in your school time. Now if I write something as 7 to the base 10, this means the number is in decimal format. If I ask you, can you convert this into its binary equivalent, that is basically the number in its binary format, that is base 2. How can we do that? It's a very easy thing. You must have done it in your school days. What we do is, we take 7 and we divide it by 2. Whatever is the remainder, we write it. So the remainder is 1 because 2 into 3 is 6 and there is a remainder of 1. So 2 into 3 is 6. So we write 3. Again we take 2 and we divide it. So again if I divide, the remainder will be 1. So this time 2 into 1 will be 2, right? So this is what I write. So the moment I reach 1, I will stop. And then I'll start writing from the bottom till the top. So what do I get? I get 1, 1, 1. So this is the binary equivalent of this number in decimal. Got it? Let's take one more example. Probably we will take 13. If I ask you 13 base 10, what will be its binary equivalent? You can try that out. It's going to be very simple. You take 13, you divide it by 2. Again, 2 6 are right? So the remainder will be 1. Again, you divide it by 2. This time, the remainder will be 0 because 2 into 3 is 6. Again, you divide it by 2. This time, 2 into 1 is 2. So the remainder will be 1. The moment you reach 1, you stop. You can again start writing from the bottom till the top. That's 1, 1, 0, 1. So this is how you convert a decimal to a binary. Now, it's very simple. If I ask you, how do you convert it in the opposite manner? Let's understand that as well. So if I take it 1, 1, 0, 1 in the binary, if I ask you what will be its decimal equivalent, you know it, right? Because we just now did it. The opposite will be 13. So you can straight away write 13. But how did we get it? It's very simple. How it works is, you start from the right and you move on to the left. You start from the right and you move on to the left. And the indexing goes as 0, 1, 2, 3. Got it? What is the first number on the right? 1. So you take 1 and you multiply that with 2 raised to the power of the index. Done. After this, you again take the next one, that's 0 into 2 raised to the power of index. That's 1. After that, you again take 1 into 2 raised to the power of index. After that, you again take 1 into 2 raised to the power of index 3. Got it? Once you've done this, you add them up. So on adding, what you'll get is, this will be 1, this will be 0, this will be 4, and this will be 8. So the summation comes out to be 13, which is basically the decimal equivalent of this binary number. Got it? So quite simple. Just remember, you start from right and then you move on towards the left. So we know how to convert a decimal to a binary. Can I write a function that will take a decimal and give its binary equivalent? Probably yes. Let's try writing it. I'll be returning a string. Why a string? Like the best data type that I can think of as string. You can probably think of list as well. That depends on you. Convert to binary. I'll be taking the integer x. What am I doing? I'm basically dividing it by 2, dividing it by 2, dividing it by 2 till it reaches 1. That is something I'm doing for sure, right? The first thing I can do is, okay, while probably this can be n is not equal to 1, I will keep dividing it by 2. Quite simple and straightforward. The division will happen. After division, what am I doing? I'm picking up these remainders and I'm going from bottom to up. So maybe while the division happens, I can store the remainders. I can. So I'll take a res and I'll initialize it empty. It's a string. And what I will do is, I'll say, hey, if n modulo 2 equal to 1, that means on division, if it leaves a remainder of 1, I will say resultant, can you add yourself a 1, right? Or else, hey resultant, please add a 0 to yourself. But what will happen if I do this? In this case, first 1 will get attached, then this 0, then this 1, then this 1. So you'll get something like this, which is not what you want. You want it in the reverse manner. Reverse manner, yes. So please make sure after the while loop is completed, reverse the resultant string. And once you've done it, you can return this resultant. Done and dusted. This is a function which is going to take any possible integer and it's going to give you its binary equivalent in the format of a string. You can do it in terms of list or any of the data types or data structure as you wish to. So what is the time complexity? Can I analyze the time complexity? It's very simple. I'm dividing it by 2, dividing it by 2. If you would have seen my binary search videos, you know, right? Logarithmic base 2n. When you divide it by 2, it's always logarithmic base 2n. Got it? What about the space complexity? It's again logarithmic base 2n. Why? Because the number of steps I'm taking, the number of remainders will be same. Whatever number of steps I'm taking, the number of remainders will be same. And that is the space that this resultant string will take. Right? 4. Quite simple. So this will be the time complexity and the space complexity if you are looking forward to convert a decimal to a binary. So try to try out the reverse one as well. That is converting the binary to its decimal equivalent. So it'll be given a string and it'll have to return an integer, correct? So returning an integer, convert to decimal and you will be given a string, right? So let's assume string x. Now what is the first thing that you would be doing? You'll be traversing in the backward direction, correct? Starting from this one, then going to this, then going to this, then going to this. Correct? So you'll be traversing in the backward direction. So let's do that. So I'll be like, okay, what is the length of the string? X dot size or length, depending on whatever programming language you're using. After this, what will you be doing? You'll be running the reverse for loop. So that basically starts from length minus 1 and goes till 0th index. Correct? Now what am I doing? I'm taking whatever it is. If it is 1, I'm taking it, right? And I'm multiplying that with 2 raised to the power something, right? After that, I'm multiplying it with 2 raised to the power 1. After that, 2 raised to the power 2. So every time there is an increment or a multiplication of a power of a 2, correct? So what is the initial power of 2? If I ask you power of 2, P2, let's say power of 2. Can I say initially it's 2 to the power 0, which is 1. Power of 2 is 1. And the number that I'm looking for initially is 0. I'm very sure about that. So what will I do? I'll say, okay, hey, listen. If x of I is equal to 1, if that character is 1, because that has to be 1, be very sure about one thing. If the character is 0, doesn't matter what you're multiplying it with, it will always be 0, correct? So only if it is 1, in that case, you'll say, okay, number plus, you're multiplying 1. Multiplication of 1 with anything doesn't. It's just this power of 2 that you'll take. It is just the power of 2 that you'll take. So number plus power of 2, correct? And for the next step, the power of 2 will be power of 2 multiplied with 2. Understood? Right? So what this does is, initially you start with 1 and then you multiply 2, you automatically get 2. After that you multiply 2, you automatically get 4. After that you multiply 2, you automatically get 8. You don't have to compute 2 to the power 3, you don't have to compute 2 to the power 2. Because it's an increment power of 2. Got that? Once this is done, what you can do is, you can go ahead and return the number. Done and dusted. What will be your time complexity? Can I say your time complexity will be big O of the length of the string? And what will be the space complexity? It's going to be a big O of 1 because I'm just storing it in an integer, correct? So this is how you convert a binary to its decimal equivalent. So we know how to convert a decimal to a binary and a binary to a decimal. And I won't be doing anything else like all the other thing like octal and hexa and all the other conversions. The reason being, this is the only thing that we'll be requiring for solving problems in DS algo. So let's understand one thing. When I write something as int x equal to 13, does the computer really store 13? It doesn't. Why? Because the computer only understands 1s and 0, right? It doesn't understand something like 13. So what happens behind the scenes is, this 13 is converted into its decimal equivalent, which is 1101. That is the decimal equivalent. Does it store 1101 base 2? No, it doesn't. Why? Because there is something as integer. Whenever you write something as integer, it means 32 bits. The computer stores 32 bits in its memory. But this is nothing but 4 bits. What about the other 28 bits? What happens is, they fill themselves up with zeros. So this is the rest 28 bits. So overall, the computer stores this one. Yes, this is what the computer stores in its memory because it only understands 1 and 0. Now, whenever you're trying to read x, assume you say print of x. Why is 13 getting printed? What happens is, the reverse conversion happens. Gets converted into the decimal and then it is printed. So the computer never stores the decimal. It always converts the number into the binary and then stores it. Remember this. Now you might be thinking, okay, integer is 32 bits. What about the other? So long is 64. So I won't be going for long because most of the problems you can solve it with int, and whatever concepts I'll be teaching with integer, and they can be applied to long as well. It can be just extended because the concepts are same. The only difference will be 64 bits. I'll be teaching in terms of 32 bits. You can extend it and apply it to 64 bits as well. So before getting into the bitwise operators and the problems, we'll be learning about 2 more concepts. Again, it won't be required in problem solving, but it is just good to know. The first one is 1's complement. Imagine I give you a number 13 and I ask you, hey, what is the 1's complement of 13? So what you do is, you basically write it in terms of binary. 1101 is the binary. Once you have written that, you convert that, like you flip all the bits. Yes, you'll be flipping all the bits. So once you flip all the bits, you'll have something like 0, 0, 1, 0 in terms of binary. And this is your 1's complement. Got it? Now 2's complement is super simple. The step 1 of 2's complement is figure out the 1's complement of the given number. And the step 2 is add a 1 to it. Add a 1 to it. Quite simple. So if I ask you, hey, 13's 2's complement. It's very simple. You convert 13 to its 1's complement. Once that is done, you add a +1 to it. Again, you might not have done binary additions, but just take it as a thumb rule as of now. So what you basically write is 0, 0, 1, 0. You add a 1 to it. So when you add a 1 to it, this will be zeros because if you don't give anything, that is basically considered as 0. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. Just as of now, do not think about the addition. Just understand this, that you add 1 to it. In the next step, I'll be teaching about the addition operator. Over there, you'll understand the rules as well. So this is your 2's complement. Very simple. Figure out the 1's complement, add a 1, get the 2's complement. Super simple. Got it? So we need to learn about the operators that we will be using in bitwise manipulation. Why? Because without operators, you cannot solve problems. So we'll be learning about AND operator, OR operator, XOR operator, shift operator, and the NOT operator. So let's get started, and I'll be starting off with the AND operator. Very simple. AND operator, probably I'll just start over here. AND operator means all true means true. One false means false. Remember this. What does this mean? So if I write something as x equal to 13 and 7. So what happens in the background is 13 is converted into its binary, which is 1, 1, 0, 1. Again, 32 bits because it is integer. So you'll always have 0, 0, 0, 0, something like that. But I will not be writing it because zeros, they don't come into picture that much. What is 7? 7 is 1, 1, 1. That is 7 if you try to convert it into binary. Again, 0, 0, 0, 0, 0. Around 29 bits of zeros. So you do an AND with it. So again, you can fill this with 0 because there's nothing. So when I say all true, all means in this particular row, there might be another number, 9. There might be 4 numbers that you're doing AND with. Whatever, if there is 1 over here, all has to be, like all of them has to be 1. Then only you can write a 1. So both of them are 1, so I write 1, right? Over here, there's 1 false. 1 false means I'm done. I'll be 0. 0 means false, basically. Over here, all of them are 1. 1 means true, yes. Over here, 1 is false. So you put a 0. Again, all of these will be 0 because when you do 0 and 0, you'll get 0, right? So I'm not writing again. So this is your binary when you do an AND. And what is this number? This is nothing but 5, yes. So the resultant that you will be getting is 5 when you do an AND operation. I hope you have got the AND operator. So AND operator is done. The next one is OR operator. Now when I say OR, it means one true means true. All false means false. Got it? So when I say x equal to 17, the sign of OR is this one. It's a pi. 17, or rather let's say 13. 13 pi 7. So again 13's binary is 1, 1, 0, 1. 7's binary is 1, 1, 1. So when you do an OR, so let's do an OR. So when you do an OR, which is basically the pipe operator, you at least have 1 true, right? So you at least have 1 true. You at least have 1 true. Over here there's a 0. You at least have 1 true. And the remaining bits are 0, so you don't care about that, right? So this is your equivalent. And how much is that? Quite simple. This is 1, this is 2, this is 4, and this is 8. 8 plus 4, 12, plus 2, 14, plus 1, 15. So that's 15. OR operator is clear, right? So what is the next one? XOR. So let's understand the XOR operator now. So XOR operator is very simple. If you have number of 1's as odd, you'll always get 1. If the number of 1's are even, you'll always get it as 0. Remember this. So if I say x equal to 13, the symbol of XOR is this, 7. 13 is 1, 1, 0, 1. 7 is 1, 1, 1. And if I do a XOR, which is this, how many 1's are there? 2, which is even. So this will become 0. How many 1's are there? 1, which is odd. So this will become 1. How many 1's are there? Oh, my bad. This will be again 0. If this is 0, this is going to be 1 because odd. And over here, there are 0 1's. So 0 1's means even 1's. Again 0. So technically all will be 0. So this is the number that you will get. And what is the value? The value is 10. Because if you try to convert this into its decimal, this is 2, this is 8, and rest of all are 0. So 8 plus 2 will be 10. So 10 is what you will get. So you're done with the XOR operator as well. The next one is shift. So we're done with the XOR operator. Now it's time to understand the shift operators. So let's start with the first shift operator, that is the right shift operator. There's one more, that is the left shift operator. We'll come to that afterwards. So we write something as x equal to 13 right shift of 1. So this is the symbol of right shift. So we write something as 13 right shift of 1. You can write it 2, you can write it 3. What does it mean? 13 means 1, 1, 0, 1. That is in binary. And there are zeros. Right? Lots, 28 zeros on the left. So when I say right shift by 1, it means this one goes off the cliff. Yes, this will go off the cliff. And the 0 will be here. This one will be here. This one will be here. What about the rest? There were zeros, right? Again, this 0 will be here. This 0 will come here. So technically, there are all zeros on the left. So this is what happens. Yes, this is what happens. And what is this number? This number is nothing but 6. So you get something as 6. Keep this in mind. It is going to be helpful as we move forward. Let's do one more thing. Let's say x equal to 13 right shift of 2. Okay. So again, that's 1, 1, 0, 1. When I say right shift by 2, this will go off the cliff and this will go off the cliff. 2 places. So this will come to the right. This will come over here. This 0 will come over here. This 0 will come over here. Again, this will be filled with zeros. So what's this number? This number is 3. Again, keep it in mind that this number is 3. I can probably say x equal to 13 right shift of 4 as well. I can say that as well. So if I say that, what will happen? I have something as 1, 1, 0, 1. How many will go off the cliff? All of them. All of them. And this 0 will be here, this 0 will be here, this 0 will be here, and this 0 will be here, and then continued. So it'll be 0 technically. You're getting how the right shift works, right? So there is a very simple formula to get this value. It's very, very simple. So if I say 13, or if I say by that reason, x right shift by any number k, it basically means x divided by 2 to the power k. Yes, that is how the formula is. And I can prove it. I'll give you the proof as well. But before that, let's work on this. So 13 divided by 2 to the power 1, which is 6. Right? 13 by 2 is 6. 13 divided by 2 to the power 2. That's basically 13 by 4. That's 3. 13 divided by 2 to the power 4, which is 13 divided by 16, which is 0. Works. Why does it work? So I'll take a very small example. This one in order to explain why does it work. So I'm saying 13 right shift of 1. So let's understand what is 13 initially. 13 is 1, 1, 0, 1. Let's try to write down it in terms of the decimal conversion. That's 1 into 2 to the power 3. That's 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. Agreed? Agreed though. So when I say 13 right shift of 1, what is the number that I get? Or rather, what is the binary that I get? 1, 1, 0. So let's try to write it as well. 1, 1, 0 because the 0 will be here, this one will be here, and this one will be here. This is what we get. And what happens is, this one, right, this one, which is initially here, now comes one place to the right. Thereby, it ends up being 1 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0. This happens, right? And this is off. This is off. This is off the cliff. So technically, this is off the cliff, right? And this number is same. This number is same. This number is same. What has changed? Do you see something? 2 to the power 3 is 2 to the power 2. Technically, if I just take 1, 2 out of it, 1, 2 out of it, do I get this? I do get it. That is why if you are doing 1 right shift, 2 to the power k divided by 2 to the power 1, if you are doing 2 right shifts, divided by 2 to the power 2, got it? So we are done with the right shift operator. Now there's one more shift operator, that is the left shift operator. But before that, one thing. When I write something as x equal to 13, the computer stores it in terms of 1101, a simple binary, because it's a positive number. But what happens when I write something as x equal to minus 13? How does the computer store this minus? For that reason, how does the computer store this particular positive thing? We need to know this as well, right? Let me explain you. I told you that integer has 32 bits. Remember one thing, the first bit or the last bit, if you talk about from left to right, which is basically the 31st bit, that is reserved for sign. That is reserved for sign. And the rest are used to store numbers. Like in this case, it will be 0, 0, 0, and then 1, 1, 0, and 1. This is how I will be storing 13. What will be the sign? It's very simple. 0 for positive, 1 for negative. So what happens is, I say 0 over here. So this is a sign bit, and the rest are used for storing numbers. Okay, fine. What about x equal to minus 13? How does the computer store it? Very simple. 2's complement. Remember that? We're going to use that over here. So when I say minus 13, right? What we do at the first step is, we write down the simple plain positive number 13, which is basically starting from 0, goes on till 1, 1, 0, 1. So we write down the plain positive number. Now, whenever the computer has to store a negative number within itself, it converts it into its 2's complement. So we'll be converting this into its 2's complement. What will be it? You know it. First step is 1's complement, which is flipping all the bits. It's going to be 1, 1, 1, all 1's, 0, 0, 1, and 0. So 1's complement is done. Once 1's complement is done, you add a plus 1 to it. So once you add plus 1 to it, what happens is, you get 1, 1, 0, 0, and these all are 1's. And the last bit is also 1. And the last bit is also 1 because of the flip that you did. The last bit is also 1. So this will tell you that this is a negative number. And this is how it understands that if it is storing a 2's complement, it means that it is storing a negative number. So this is what will be stored internally. Got this? So now you know how to store a negative number as well. So a very simple question. What is the largest integer that integer variable can or data type can store? So can I say the last one is reserved for sign, right? So it will be 0 for sure, because 0 means positive. If I try to fill all these with zeros, will it make sense? Then the overall number will be 0. Doesn't make sense, right? So can I say this? That, okay, probably I can have 1, 1 and all filled with 1's. Yes, which is technically nothing but 2 to the power 30 plus 2 to the power 29 plus 2 to the power 28 and so on till 2 to the power 0. Can I say this? I can. Which is nothing but 2 to the power 31 minus 1. So this is the largest possible value that you can store in an integer. And this is technically like you might have seen this integer max. This is this value integer max. So the next question, what will be the smallest number that it can store? And you might think, okay, minus of 2 to the power 31 minus 1. No. Remember this, that the computer uses the last bit to understand the sign. Can I do something so that the last bit, apart from the last bit, I'm using all the bits? Probably yes. Forget about 32 bits as of now. What if I take 2 to the power 31? Okay. I say minus. So what is 2 to the power 31 in terms of bits? It's nothing but 1, 0, 0 and all zeros. These are the 32 bits. Starting with 1. As of now, I'm not thinking about sign bits. I know one thing. whenever I write a minus, the computer will never store it like this. So I'm not using the last bit because the computer will never store it like this. So I'm not using the last bit. What the computer does is, it converts it into its 2's complement. So the first, the 1's complement is inverting. So this will be 1, this will be 1, this will be 1. All of them will be 1 apart from the last. Perfect. What is the next step to get 2's complement? Add a plus 1. So when you add a plus 1, what happens? So basically what happens is, you get 1 plus 1, 0, carry over 1, again 0, carry over 1, again 0. So eventually you get all zeros, carry over 1, 0, carry over 1 and 1. So this is what you get, all zeros, yes. And this kind of tells you that, hey, listen, yeah, I'm correct. This is what you get. This tells me that this is negative. And since this is 2's complement, all of them are zeros. All of them are zeros. It kind of tells me that this is minus 2 to the power 30. All of them are zeros. Because of 2's complement, I'm able to store it. And this is what you generically say as int mean. This is the minimum value of integer that you like. This is the minimum value that you can store in an integer data type. So if you carefully see, I was using the last bit over here because I know if I take a negative number after making a 2's complement, it will work out. Because the last bit will be used to identify positive or negative. I couldn't use the last bit over here. Why? Because if I put a 1, it clearly tells me it's a negative number, but I cannot, I have to keep it 0, right? So in terms of negative number, you convert it into 2's complement. In case of positive number, you keep it as it is. So it is time to come back to the left shift operator. Let's understand the left shift operator in depth. So what is left shift operator? Again, very simple. If I say 13 left shift of 1, you left shift it. So basically it means 1, 1, 0, 1 is 13 and there will be zeros on the left. So what happens is, basically the last 0 goes off the cliff. Yes, it goes off the cliff. And this 0 will be here. This 0 will be here. This one will be here. This one will be here. This 0 will be here. This one will be here. And this will be filled with 0. This will be filled with 0. So basically left shifted by 1. If I try to convert it, it's going to be 26. You'll figure it out to be 26. Again, why? Very simple reason. If you try to write it down, it's this one is going to contribute for 1 into 2 to the power 3. This one for 1 into 2 to the power 2. This 0 for 2 to the power 1. This one for 2 to the power 0. If you try to take this, it will be 1 into 2 to the power 4. This one will be 1 into 2 to the power 3. This 0 will be 2 to the power 2. And this 1 will be 2 to the power 1. And this 0 never contributes. So it doesn't matter. Again, if you carefully observe, there is an increment of power of 2. So technically, whenever I'm saying a number left shift by k places, it means number multiplied by 2 of k. That is what I did. 13 into 2 to the power 1 was 26. Got it? Now you might have a question, hey Striver, what if I take the biggest number, which is 2 to the power 31 minus 1? That's technically all ones. That's technically all ones, right? Apart from the last bit, all ones. If I take this number and I say left shift of 1, so what happens is this 1 tries to go to the left. It cannot because it will overflow. So this is a case of overflow. So remember, there can be overflow. You'll get weird numbers. So whenever you are doing a left shift, you'll have to do it in terms of that boundary. What is that boundary? That boundary is this particular number because this is the maximum it can store. You cannot go beyond it. Got it? So we are done with the shift operator. Now it's time to understand the NOT operator. Now it's interesting. Again, 2's complement will be involved. So the NOT operator is nothing but the tilde that you see basically below the escape button. So imagine I write something as x equal to NOT of 5. How it works is, first step is very simple. It will flip. The second step is, it will check if it is a negative number or not. If it is, then it will store the 2's complement, or else it will stop. This is how the NOT operator works. Let me explain you. So when I say 5, how does the computer store it? The last bit is the sign bit. So this is the sign bit, and then 0, 0, 0 and a 1, 0, 1. This is technically the binary, right? Whenever I say something like flip, first step is flip, because I'm applying NOT operator. Flip it. So if you flip, the sign will flip to 1. This will be 1, 1, 1, 0, 1, 0. Perfect. Flip is done. Now what is the next thing? Check negative. Is it negative? It is negative. If it is negative, convert this to its 2's complement, because it's a negative number. You already know it's a negative number. Convert it into its 2's complement. Okay, let's convert. First step, 1's complement. 0, 0, 0, 1, 0, 1. Done. Next step, plus 1. So let's do a plus 1. 1 plus 1, 0. Carry over 1, 1. Again, 1 goes as 0, 0, 0, 0, 0. And the sign bit. So what is the value? Sign bit says minus. And this entire thing is 6. So it is minus 6. This is what the computer will store. Got it? Minus of 6. This was about positive number. What if it's a negative number? Let's understand super quickly. X equal to naught of minus 6. First of all, how does the computer store minus 6? It stores it in its 2's complement format, right? So I'll be storing, like if I write this, this will be minus 6. I'll be storing minus 6 in terms of its 2's complement format. And what is that? First of all, what is 6? That's 0, 0, 0, dot, 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 1, 1, 0. Agreed? What is the 1's complement? You flip it. 1, 0, 0, 1, 1, 1 and all 1's. So what is the next step? You'll have to add plus 1 in order to make it its 2's complement. So if you add a plus 1, 1 plus 1 is 0, carries over 1, 1, again is 0, again a 1, 1, goes over till this. So this is how the computer stores minus 6. So now we have to apply a NOT operator. What is the step 1? Flip, flip, flip. Okay, we'll flip. The sign bit. The sign bit will go as 0. These all are 1's. So the 1's will turn to 0, 0, 0, 0, 0. This 0 will turn to 1. This 1 will turn to 0. This 0 will turn to 1. And this is how it is. What is the next step? Check if it is negative. No, it is not negative. It is not negative. So what do? I stop. What is the number? It's a positive. And this number is 5. So you got back the number. Quite simple. Always remember, if you're doing operations on a negative number, first step is convert the negative number into its 2's complement, because everything is done on the 2's complement, because that is how the computer stores. The computer will never store minus 6. It will always store its 2's complement. Got it? I hope this is clear. So I can say I'll go up and I can say that with this, the operators are completed. So with this, I'll be wrapping up this particular lecture. In the next lecture, I'll be covering up a lot of things. In case you've understood everything, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I will be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.